Transformers are the engines behind modern AI, and they're brilliant predictors. But they have a quiet weakness. They don't naturally compress what they've seen into a tidy internal picture of the world. A new paper from Microsoft Research fixes this with a surprisingly small change to training. It's called Next-Latent Prediction or NextLat, and the whole idea fits in one line. Don't just predict the next token, predict the next latent. Let's unpack what that means and why it helps so much. Start with a contrast. An older kind of model, the recurrent network, processes text one step at a time, squeezing everything it has read into a single small state, which it updates with a fixed rule. That state is forced to be a compact summary. A transformer works completely differently. It keeps every past token around and, using attention, just looks up whatever it needs on demand. That's enormously powerful and parallelizable, but notice what's missing. Because a transformer can always look up the raw past, nothing ever forces it to summarize. There's no pressure to build a compact state with consistent update rules, so it tends to learn task-specific shortcuts, little tricks that fit the training data but fall apart on new situations. Researchers call plain next token prediction myopic. It's short-sighted, and it's especially weak at planning and multi-step reasoning, where you really need a stable internal model. So here's the wish. Could we give a transformer the recurrent network's good habit, a compact, consistent internal state, without giving up the things that make transformers great, parallel training and fast inference? The author's answer is to leave the architecture completely alone and change only the training objective. Add one extra goal during learning, and let the network discover the discipline on its own. That extra goal is Next-Latent Prediction. Alongside the usual job of predicting the next token, the model is also trained to predict its own next hidden state, its next latent, given the next token. In other words, it has to anticipate where its internal representation will go. This is a self-supervised target living in representation space, not just in the space of words, and it changes what the model is rewarded for keeping in memory. Here's the contrast with related methods, all in one picture: standard next token prediction, and even multi-token prediction. Supervise the model only in token space, on the words it outputs, leaving the intermediate representations to fend for themselves. NextLat adds supervision directly on those internal latents. By pairing sparse one-hot word targets with dense, continuous latent targets, it gives the network a far richer learning signal. How do you predict a latent? With a small helper, a three-layer network they call the Latent Transition Model, PSI. It takes the current hidden state and the next token, and it predicts what the next hidden state should be. Effectively, it learns the model's own internal dynamics, the rule for how one mental state flows into the next. It's an RNN-style update rule, bolted onto a transformer purely as a training aid. Training it has two parts. The first is straightforward: make the predicted next state match the real next hidden state, measured with a smooth L1 loss. But there's a classic trap in self-prediction. The model could cheat by collapsing every state to the same constant vector, trivially predictable and useless. The fix is a stop gradient on the target, which blocks that degenerate shortcut and keeps the representations meaningful. They don't stop at predicting one step ahead. They roll the little transition model forward over a horizon of several steps, feeding in the upcoming tokens, and supervise every predicted state along the way. Interestingly, the theory says the key benefit, belief states, already appears with just a single step. The multi-step rollout isn't strictly necessary, it simply provides a richer, denser training signal. The second loss ties the imagined states back to reality. It takes the predicted hidden state, runs it through the model's frozen output head, and checks with a KL term that it produces the same next word distribution the real state would. This is essentially knowledge distillation aimed inward. It forces the predicted latent to be not just numerically close, but functionally equivalent, leading to the same predictions. Now the theoretical heart of the paper. The authors prove that, under this objective, the model's latents probably converge toward belief states. A belief state is a precise idea from reinforcement learning. It's the compact summary of everything in the past that is actually sufficient for predicting the future. Nothing more, nothing less. And that compressed, sufficient representation is exactly what robust planning and generalization require. This isn't pulled from thin air, it borrows from reinforcement learning. An agent acting in a partially observed world can't see the full state, so it learns a belief state, a running summary of everything observed so far that's sufficient to act well. A line of work called self-predictive learning builds those summaries by having the agent predict its own future representations. NextLat imports that exact trick into language modeling, treating the text as a stream of observations and the hidden state as the model's belief about what's really going on underneath. The elegance is in what doesn't change. The transformer's architecture is untouched. Its inference procedure is untouched. Its prized parallel training efficiency is untouched. NextLat adds only a lightweight auxiliary loss during training, and the helper network can be discarded afterward. It injects the spirit of recurrence, a recurrent inductive bias, without any actual recurrence slowing things down. There's another reason this helps, about the quality of the training signal itself. Ordinary next-token prediction gives the model a single, sparse target per step, one correct word out of tens of thousands, a thin sliver of feedback. NextLat adds a dense target on top, a whole continuous vector, the next hidden state that the model must match. That's far more information per token. So beyond the belief state argument, NextLat is simply more data efficient, squeezing more learning out of every example it sees. Theory is nice, but does it help in practice? The authors test NextLat across 4 arenas: world modeling, reasoning, planning, and ordinary language modeling, plus a bonus on inference speed. Across the board, the same small auxiliary loss delivers real, often large gains. Let's look at the highlights. The most vivid result: they train models on sequences of Manhattan taxi trips, then ask each one to reconstruct the city's street grid purely from its learned internal states. A standard transformer produces a tangled, inconsistent mess. NextLat produces a recognizably coherent map of Manhattan. Even where it's imperfect, the errors are sensible. It genuinely built an internal world model. That map is the whole thesis made visible. The taxi data never hands the model a map. It only ever sees individual trips. To reconstruct the grid, the model has to infer the underlying structure of the city and represent it consistently. The standard transformer never bothers. It just memorizes local trip statistics. NextLat is pushed to find the real, compact structure underneath. On reasoning, they use countdown, a numbers puzzle so hard that even GPT-4 solves only a few % of instances by default. The goal is to combine given numbers with arithmetic to hit a target. A plain transformer of this size lands around 33%. NextLat jumps to roughly 55 and up to nearly 59% with the multi-step version. That's a dramatic gain from a single auxiliary objective. Planning is where the difference is starkest. This is the path star task, a center node with several arms, where the model must produce the path to a goal. It was designed specifically to expose the short-sightedness of next token training, the shortcut that works during teacher-forced training but fails at test time. And the baselines fall right into the trap. Their solve rates collapse as the graphs grow. NextLat, by contrast, stays close to 100% across every graph size tested. Because it's been forced to maintain a coherent belief state about the whole structure, it doesn't rely on the brittle local shortcut. It actually plans. On ordinary language modeling, the gains are subtler but telling. They freeze the hidden states and train simple probes to read off tokens, several positions into the future. NextLat states carry far more information about what's coming than a standard transformers. The representations aren't just good for the very next word, they genuinely look ahead. A close cousin of planning is length generalization, solving problems longer than anything seen in training. On a hard algebra word problem benchmark, standard transformers degrade as the problems grow, while NextLat keeps going. The authors frame this beautifully. It's like getting the generalization benefits of training a recurrent network, but without the recurrent network's slow, sequential training. And there's a practical bonus. Since the little transition model can imagine the next few hidden states before the full transformer runs, you can use it to speculate several future tokens at once, a flexible, variable-length form of self-speculative decoding. This chart shows how often those speculated tokens are accepted. The same machinery that improves reasoning also speeds up inference, at no extra cost. What's neat is that this speedup comes for free. Other speculative decoding methods need a separate draft model, or extra prediction heads bolted onto the network. NextLat's transition model is already there from training, and it's tiny. So you get faster generation without any new components, just by reusing the dynamics the model already learned. Here you can see it drafting several tokens ahead, with accepted ones in green and the occasional rejection in red. It's worth dwelling on why this look-ahead is flexible. Earlier multi-token prediction schemes commit to a fixed number of future tokens. You always draft, say, 4 ahead, whether the model is confident or not. NextLat instead rolls its transition model forward recursively, one imagined state feeding the next, and can stop whenever its confidence drops. So on easy, predictable stretches it leaps far ahead, and on hard ones it stays cautious. The number of tokens it speculates adapts to the text, which is exactly what you want. Step back and look at the full ledger from one small change. More coherent world models, higher reasoning accuracy, robust planning where baselines fail, better generalization to longer problems, representations that look further ahead, and faster decoding on top. All of it flows from a single auxiliary loss that asks the model to predict its own next latent state. The authors carefully take the method apart to see which pieces carry the weight, and the results are instructive. The stop gradient is essential, remove it, and the representations collapse. Exactly the failure mode it was designed to prevent. The KL loss, the one that grounds predicted states in real token distributions, gives a clear and consistent boost, and the latent prediction and token prediction work best together, not as substitutes. It's not a bag of tricks where one part does all the work. The components genuinely complement each other. A few caveats keep it grounded. The auxiliary objective introduces extra knobs to tune the smooth L1 term, the KL term, and the stop gradient configuration, and the paper's ablations show these choices matter. The belief state guarantee is a theoretical limit the training moves toward, not a certificate for any finite run. And while the results are strong on these focused benchmarks, demonstrating the same gains at frontier scale is still future work. Here's the through line. In trading recurrence for attention, transformers quietly gave up the recurrent network's compact internal model of the world. NextLat hands it back. By simply asking the model to predict its own next latent, it pressures the network to compress the past into belief states, just enough information to see the future clearly. And the result is better reasoning, planning, and generalization, plus a speed bonus, almost for free. Sometimes the best upgrade isn't a bigger model, it's a smarter thing to learn.